Hello, everybody. Thank you all for sparing some time to attend today's talk, which is part of the More You Know webinar series by SPWLA. My name is Ali Tinni, and I'm a faculty in the Petroleum Engineering Department of the University of Oklahoma. For today, I'll be presenting you several NMR applications to Shale EOR evaluations. So we will essentially see how NMR can be beneficial in EOR studies in unconventional shales and why maybe NMR might actually be very critical in order for us to better understand EOR in shales. Today's talk is sponsored by Green Imaging Technology, which is a company that not only makes NMR softwares, but also provide NMR solutions for oil and gas applications. As a matter of fact, all the data sets that I will be presenting you today have been acquired with green imaging softwares. These data sets have been acquired by graduate students, both current and former students here at the University of Oklahoma, but in particular in the Integrated Core Characterization Center of the University of Oklahoma. More details actually about the current research in the Integrated Core Characterization Center, as well as green imaging technology, can be obtained on this website, usgc.ou.edu for the Integrated Core Characterization Center and greenimaging.com for green imaging technology. All right. So now we can move on and actually start our talk. But before we actually get into the actual NMR applications, it might be beneficial to review actually why do we even do EOR, or why are we even interested into EOR in shales in the first place, right? And so we can see on this figure by the EIA, what we see over here is actually the oil production per well in several unconventional shale plays, right? So we are looking at here the Niobrara, the Bakken, the Anadarko Basin, Permian, and Eagle Ford over here. And so it seems like regardless of the shale play location, one thing that is very common in all these shales is that we observe a very steep decline in all these wells really very, very early on, right? So we do see quite a bit of decline in the first 12 months. So we do lose, I would say, a good probably here about 80% or so. At least I would say a good 70% of production is being lost within the first 12 months, right? And so due to this loss in production within these first 12 months, it means that operators have to be really innovative about the kind of solutions that they are going to implement to sustain production. And that is where EOR comes into play. EOR methods do come into play because EOR allows you, or enhanced oil recovery, allows you to actually maintain your production, or actually sometimes even increase it compared to the previous cases where you haven't really implemented EOR. And so if we look at this, is actually an example of Eagle Ford of EOR in the Eagle Ford. This happens to be a half and puff EOR, gas injection half and puff EOR, which is the preferred EOR method in unconventional shales. So the half and puff EOR process is a process where you do inject I would say the recovery agent. It doesn't really have to be a gas in order to be a half and puff process. However, once it comes to shales, we do use gas as an recovery agent. So in the half and puff process, you will inject a recovery agent, allow it to contact the formation for some time, which is known as a soaking time, and then you're going to produce, you're going to open the well back and produce hydrocarbon, hopefully, within using the same well, right? So the half and puff process is a process which can utilize a single well. You don't need to have multiple wells in order to do a displacement like in a displacement scenario. So the half and puff process is different in that regard. So coming back here to the Eagle, for example, here we're looking at a well that was drilled, I would say probably in the second quarter of 2012. And then this well peaked within the third quarter of 2012. After that, we see this pretty steep production decline as expected based on the previous slide. And around the third quarter of 2014, the company that owned this well decided to implement a half and puff EOR project. And so here you see the production went down to zero. That is where they were injecting actually natural gas in this formation. So they injected for about 6 months before opening this well back. So here we can see when when the well has been opened back, you can see the production really recovered quite a bit. And then we see a steep production decline, even steeper than previously. And so then the company went back, injected, produce, inject again, and produce. So we can see these cycles of injection and productions, and this is a typical cyclic half and puff process. This will really be a poster child of that. And when we look at the same graph, but now in a cumulative manner, we can see this purple dotted line will represent the recovery that would be expected in case EOR was not implemented. However, this green line over here shows actually recovery, shows the actual recovery after EOR has been implemented. So we can see 30% more hydrocarbon has been recovered, which is actually a pretty good thing. So EOR is something that can definitely work in Shale. However, before we engage in an EOR project, there are quite a bit of studies to do to evaluate the feasibility and to evaluate some operational parameters such as injection pressures, injection gas, soaking time. So there are many things to figure out before we engage into an EOR project in shales. Right. And so once it comes to the evaluation process, the first thing that we generally do is to do a laboratory evaluation, right? And this lab evaluation is done in order to understand operational parameters such as soaking time, injection pressure, gas type, and also to identify the recovery mechanism. Try to understand what will be these recovery mechanisms that will be driving this fluid recovery process. Once these parameters are known and understood, then we can engage into reservoir simulation, where different scenarios, various scenarios can be evaluated. But in reality, the reservoir simulation also feeds back into the laboratory evaluation by providing the type of experiment to conduct, right? So very often the lab experiments that should be conducted will be based on the scenarios which are based on also reservoir simulation. So there is this kind of feedback loops, that goes between the lab and the reservoir simulation. But for this particular talk, I will focus a little more on the lab side of things because that is where NMR is very, very useful. Once it comes to half and puff EOR experiment in the lab, it can be implemented according to various specs, but essentially all half and puff apparatus will have this basic component, the same basic components, which will be an injection gas supply. So you do need that regardless of the setup. And we also need a pump that will be used to pressurize this injection gas in a shale sample that's actually contained within a pressure vessel. This entire system of shale included into the pressure vessel will be generally maintained at a higher temperature, at elevated temperature within an oven. And once the shell has been pressurized, then all the valves leading to the shell will be closed for some time. That will be the soaking time. And the soaking time will generally be pre-specified according to the need of the experiment. Then the production valve will be open to allow the collection of the of the fluids that have been mobilized during the half and puff process. So the experiment is very, very simple in principle, right? So it's not really something very complicated in terms of, I would say, understanding. Right? And these shell samples, which are used for EOR, can actually be native shell samples. So that means preserved shell samples, or they can be resaturated. They can be resaturated with some desired oil. Right? But very often, I would say that the native or the preserved sample is actually preferred because it contains a fluid distribution which is more representative of a natural fluid distribution compared to the resaturated sample. Right? And so now the main problem after conducting this EOR experiment is really about how can we quantify the amount of fluid, right? The fluid volumes that have been mobilized during the EOR process. And so for that, we generally have two methods, right? We can use either volumetric methods or gravimetric method. So let's review those two types of method. Here we do have a burette, and that's generally used during the volumetric method. So what labs will do is generally taking a burette and just insert it at the end of the production line in order to collect the produced fluids, and then they can just simply just read the volumes of fluid that are being produced, right? And the difference in color should indicate where the oil level stops and from where they can read also the water level. So it is also a measurement that's simple in principle, right? In principle. And so if we look at this method in a little more detail, it actually has several drawbacks when it comes to shales. Right? The small pore volumes of shales really lead to very, very small fluid content as well. And because we do have a very small amount of fluid, then the accuracy of volume measurement reduces quite a bit. And also there is the problem that a large fraction of the recovered hydrocarbons remain in the production line. So those ones will never really even reach in the first place the burette. So if they don't really reach the burette, then it's almost impossible really to get a good accurate volumetric measurements really once it comes to shale EOR. And so to overcome these limitations, some labs will actually opt to use some gravimetric method. The gravimetric method is where you do measure the sample mass before and after EOR. Uh, these measurements is really a good measurements because with these measurements you don't really have to worry about some fluids being trapped in the production line because you are measuring the actual shell samples before and after EOR. And so you don't really have to worry about anything that was not collected. So that's not really a problem. And the mass measurement is generally a very accurate measurement. We can measure using lab analytical balances. We can measure weight accurately down to 0.1 milligrams without much of a hassle. Right? However, the problem with the mass measurement is that we cannot really distinguish between water and oil, right? So we can only say that this is the mass of fluid that has been produced. And even converting that into volumes is almost impossible because we don't really know how much water versus how much oil, so we don't really know the overall fluid density that has been produced, and we don't really know also the remaining fluid density. So that's the drawback of this method. And that is where now we can start to see the value of NMR. But before we get into discussing how NMR can be useful in terms of these recovery measurements, it will be good to just go through a little introduction to NMR. This will be a very, very diluted introduction to NMR. It's not meant to go in details. For more details about NMR, I would recommend the webinar, the More You Know webinar by Dragon from Green Imaging Technology, where he was presenting about capillary pressure and NMR use for capillary pressure measurements. That was a great talk where he went more in details about NMR. But in a nutshell, really, if we want to understand what does NMR really measures, all that NMR is doing is to measure magnetization of hydrogen protons as function of time. That is literally really all that NMR does. And so one thing that's important is the fact that with NMR, oil field NMR applications, we only look at hydrogen, right? So a fluid that does not have hydrogen will be invisible to oil field NMR. So something like CO2, nitrogen will not really be visible, right? And so if you want to look at this magnetization as function of time, we can quantify it using actually CPMG measurements, which will give us NMR T2, which is the most popular NMR technique, where is it essentially looking at a magnetization decay as a function of time. But we can also measure NMR T1 times, which also now just represents magnetization as a function of time. But this time it will be really a build-up rate that we'll be looking at during an NMR T1 measurement. Right? And these magnetizations that we are measuring are actually very important in the sense that the total magnetization is proportional to the total amount of hydrogen present in a sample. And that is why NMR is really great at measuring fluid volume, because of this proportionality between magnetization and amount of hydrogen. And most of the fluids that we are interested in fluid, oil field applications do have hydrogen, right? Because these ones will be hydrocarbon and brine essentially. And one thing also that is also important is that the difference between T1 and T2 times can be used to assess volumes of water and oil. And so that is why it's also really good to make these independent measurements. Actually, most of the time we do them simultaneously. We do a T1, T2 measurements. We will talk about that a little more in the coming slides. But the difference between T1 and T2 times can be used to assess the volumes of water and oil. And that is something that neither gravimetric method or the volumetric method can give us accurately, right? So NMR will be a really, really good tool to measure our recovery factor during EOR processes. This will be the first application that we'll be going through. And before we actually look at these applications, let's discuss the instruments that we generally use for these. For low field, because for oil and gas application, we generally use low field NMR instruments, while the logging tools are generally limited to frequencies around 2 megahertz. In the labs, we can have low frequency instruments going up to 23 megahertz. Here we have a picture of 2 megahertz instrument and another picture of a 12 megahertz instrument. These instruments, even though they operate at two different frequencies, are very, very similar in during their daily operations. You really would not notice it in terms of how to run them. However, the 12 megahertz provide a significant advantage compared to the 2 megahertz in the sense that it can provide you with a much larger signal to noise ratio in a shorter amount of time. So the 12 megahertz measurements allow, the 12 megahertz instruments allow the possibility to acquire NMR data in a very, very short amount of time, and that with a really high signal to noise ratio. And so for our EOR application, we actually use both 2 and 12 megahertz, even though we focus a lot more on the 12 megahertz because we can provide us with results much faster. So now let's look at some NMR measurements that were conducted during EOR projects. And so what we are looking at over here at NMR T2 distributions, the green symbols over here, or the green circles, represents actually the NMR T2 distribution pre-EOR, before we did any EOR measurements. And the hollow circle over here represents the post-EOR measurements. So we can see that before and after EOR, we can see a reduction of the volume, right? So the volume has been reduced quite a bit. And this volume reduction had happened at very low T2 times, as well as, I would say, at T2 times larger than 1 milliseconds, between 1 and 10 milliseconds. So this is where the producible fluids will be located. Interestingly, now the difference now between the green and hollow symbols on the cumulative side of things will represent the total fluid volume produced. So it is very, very simple to estimate the total fluid volume produced from with NMR measurements. All you do is to just look at the cumulative NMR volume pre-EOR and the cumulative NMR volume post-EOR, and the difference between those two will give us actually the total fluid produced. So it is actually a fairly simple measurement. And these NMR measurements, because we are doing them on samples before and after EOR is done on the actual sample that we are taking out and doing the measurements in an NMR instrument. So that means they will not be really affected by the fact that some produced fluid might be stuck in the production line, might remain in the production line. So we don't have to worry about that. And these NMR measurements are actually fairly accurate because we can measure fluid volumes really accurately down to, I would say, within plus or minus 0.05 milliliter. We have found a very good accuracy. Right. Now, to go from just a total fluid volume to now separating that into water and oil, we generally use what we call T1, T2 maps, right? These are simultaneous T1 and T2 measurements. On these maps, you will have T1s on the y-axis, generally speaking, and T2 on the x-axis. And this line over here, this diagonal, the first one represents a line where the T1 over T2 ratio, the T1 time over T1 over T2 time is equal to 1. And the second line represents a T1 over T2 equal to 10. And so what we see on these lines is that we are looking at two amplitudes over here. And from previous studies and other publications, we know that the amplitude at low T1, T2 ratio will actually be water. That will be our formation water. And the amplitude at higher T1, T2 ratio will be hydrocarbon. So we can clearly see that this sample that we've used for EOR initially contained both. It contained water and oil. And now post EOR, now we can see a reduction in both amplitude, which tells us that we have produced both oil and water, right? And we can see that actually the oil that has been produced was the oil that had a slightly larger T2 times, right? That was the one that was close to the T1 over T2 ratio equal to 10 line. And the remaining one will have a higher T1, T2 ratio, right? Compared to the T1, T2 ratio of 10. And so what this tells us is that the remaining hydrocarbon will probably have a composition that's different than the initial hydrocarbon. So now we can start to see that the EOR process leads to some kind of fractionation. In this case, the remaining hydrocarbon will definitely be more viscous. So even beyond allowing us to quantify the volumes of oil and water, NMR allows us to even start to understand how will, the viscosities, for example, of the remaining fluid. So we can even go beyond that in our interpretations. Right? So NMR T1, T2 maps are really useful in the sense that they allow us to quantify oil and water. Okay, thank you. Now let's review a few applications of a few NMR applications to eager for EOR studies. So now I'll be showing you some data that have been acquired during half and puff EOR projects that we conducted on crushed rock samples. These measurements have not been conducted on solid plugs. The crushed rock methodology is actually really nice because it allows you to do measurements really fast, obtain quick measurement that allow you to do lots of studies, lots of sensitivity studies. So these crushed samples had a particular size of about 7 to 8 millimeter. And the injection gas over here that we use was 72% methane, 28% ethane, and the injection pressure was 4,400 psi. This blue curve represents the native NMR spectrum because this was a preserved rock sample. And so we can see had a bimodal distribution over here. After the first cycle of half and puff EOR, we can see that we produce essentially out of the larger T2 times. A classical NMR interpretation will tell us that we have produced essentially from larger pores, but in shells it might be a little more complicated than that. So the conversion from a T2 time to pore size is not as straightforward. But essentially it came out of pores out of T2 times larger than 1 milliseconds. For the second cycle, we didn't produce much. This is the spectrum that we obtained after the third cycle, fourth cycle, and fifth cycle. So you can see that with NMR, we can get this level of details and we can quantify at the same time our recovery. And so using this kind of measurements, we are able to evaluate operational parameters really quickly. In this case, let's review some measurement that we did to evaluate the effect of soaking time, right? That means the amount of time that we are leaving this injection gas in contact with the sample. And so now what we are looking at here is the recovery as a function of the number of cycles for a 6-hour soaking time, 3-hour soaking time in red, and 1-hour soaking time in blue. And so we can see that at a constant number of cycles, right? For the first cycle, we are definitely producing more hydrocarbon for the 6 hours. But as we start to produce some some more, and we are moving into a much higher number of cycles, now we can start to see that the 6-hour soaking time still maintains a higher production, but now the 3-hour soaking time now start to become higher than the 1-hour soaking time. So it seems like the longer we are leaving our gas in contact with the sample, the more hydrocarbon we are going to produce. And this definitely does make sense, right? However, as we are looking at this data, we started to think about the fact that the soaking time is not the only time when the gas is in contact with the sample. Even during the production, the gas is still in contact with the sample. So we decided now to create another parameter that's called the residence time. So the residence time is simply equal to the soaking time plus the production time. And so now if we take this exact same data set and we plot it now as a function of residence time instead of number of cycles, this is what we obtain. Now we can see that regardless of the soaking time, whether it was 1 hour, 3 hours, or 6 hours, all the different data sets actually follow the exact same trend, which tells us that the residence time is really the parameter that we should use to scale up these laboratory EOR experiments. And even when we are considering pilot designs, we should really be concerned about the residence time. And all this was possible by the fact that now we can actually do accurate recovery measurements with our NMR instruments. If we look at now another application where we have now evaluated the effect of the injection gas type, we are looking at still the recovery factor as function of residence time this time. And so if we look at this, we can see that the best gas to use happens to be ethane, C2. However, probably nobody will be injecting ethane because it's a pretty costly gas. But we can see that at least for scientific purposes, we know that ethane will be the best injection gas to use, and that is followed by CO2. And that is a good thing, right? Because CO2 is being considered even for sequestration in this kind of unconventional reservoir. So we can see that if we inject CO2, not only we will be producing quite a bit of hydrocarbon, but we can hope to sequester also some of it as well, sequester some of this CO2. Followed by CO2, we have the 72%, 28 methane, 28% ethane gas, which produces also quite a bit. And we can see that the worst gas happens to be the 95% methane, 5% ethane. So it seems like as we are reducing the amount of ethane and increasing the amount of methane, the gas efficiency reduces. And so we can also do this kind of evaluation. So, right. Now that we have seen that we can evaluate these operational parameters, we still want to have a better understanding of the EOR process, because this was just trying to evaluate design parameters. But we still don't know really what is really the recovery mechanisms behind this these fluid productions, right? And that can only be obtained by real-time NMR, by real-time monitoring of the EOR process, which can be achieved only with few methods. And among those ones, our preferred method is the NMR method. And so how do we do that? For that, we now take advantage of non-magnetic pressure vessels, because these type of pressure vessels, generally made out of zirconium oxides, are non-magnetic, so they can be inserted into NMR instruments. So we'll insert that into an NMR instrument, and we can just pressurize now our samples with our injection gas using these pumps, and pretty much watch the recovery happening in real time. So it allows us to watch the recovery process in real time under high pressure, high temperature. We can do these measurements under both conditions. So with this kind of setup, we can do a direct fluid estimation, right, without even taking the sample out. Right? And we can also study really the dynamics, really these details about the dynamics between the injection gas and the fluid within the rock matrix, which is very, very hard to understand really if you're only looking at the fluids which have been produced. Now we can look at inside the rock and try to understand what is happening really. Right? And with this kind of knowledge, we can start to understand the recovery mechanisms. Now, let's look at an example of such measurement. This happens to be a real-time NMR monitoring where we are looking at recovery as a function of time. Now, this happens to be in days over here that we are looking at it. And so we do see that we have produced continuously, and we had a little gap time over here. That's when we were recalibrating our NMR instrument and taking care of some tunings. And we have recovered up to about 40%, up to about 40% hydrocarbon. So it's actually a pretty good recovery. However, this does not tell the entire story because I did not show you yet the pressure profile that led to this hydrocarbon recovery. If we look at this pressure profile, this is what we have. So these dotted lines represents the pressure profile that was applied during these measurements. And so we can see that we have applied actually a gas pressure of 3750 psi during our first cycle, then 4250 psi, and that was followed by 5000 psi and 5000 psi again. And so what do we see on these ones? We do see that if we go back to the first cycle, is that even during the injection phase, which is this phase over here where we are building up pressure, and the soaking phase, as well as the production phase, we are producing during this entire time, including even during the injection phase, which is something that we did not really anticipate to see. Because if you remember, the entire definition of the half and puff process is what? You inject a gas, you allow it to contact your sample and penetrate inside the sample and interact with the native fluids, re-energize them, and then now during the production phase, you'll be producing that. That was the concept. But now what we see is that the production happens even during the injection phase. The soaking phase, we are still producing, and during the production phase, we are producing. But more interestingly, is that even in these three different phases, the trend does not change. We are still producing along the same trend. It seems like regardless of the pressure that we are, of the absolute final pressure, if it was an injection phase, a soaking phase, or a production phase, we are still producing with the same trends, which was something that kind of surprised us at the beginning, because at least we were expecting that, okay, even if we do produce during the production, and no, I'm sorry, during the injection and soaking phase, we honestly did not expect them to have the same trend as the production phase, because we expected that the production phase will show a much steeper rate, but it did not. And that shows that the recovery mechanism that was behind the injection and soaking phase is the exact same recovery mechanism that we do also have during the production phase. And that was very enlightening, because the only phenomena that can explain this happens to be diffusion, right? Because diffusion is when you do have only a concentration gradient, right? You don't really have a pressure gradient. And that's what is going to drive this recovery process, because diffusion does not require having a positive, I would say, pressure gradient coming back to the production, right? And so that was actually very good for us, because we learned from these experiments that the mechanism that we should be concerned with is not a Darcy type of flow, it's not an advective flow, it's more like a diffusive flow that we should be concerned with. And so once it comes to reservoir simulation, now we know what we should be focusing on. We should be focusing more on the diffusion aspects of things. And so to summarize this slide, with these NMR measurements, we were able to understand that diffusion is the main recovery mechanism, because the production trends observed during the injection, soaking, and production phases are all the same, which means they are all being driven by the same process, which leads to now diffusion being the main recovery factor mechanism. So now that we understand that diffusion drives the recovery mechanism, drives the recovery of hydrocarbon during half and puff EOR, it will be very important for us to simulate this process. And so to simulate this process, we will need at least the effective diffusion coefficient of gas in the oil phase in this porous media. And the first step toward getting the effective diffusion coefficient is to measure the diffusion of gas into oil in the bulk phase. That is the first step that we have to follow. And that can also be achieved with NMR measurements. And so now I will share with you some measurements that we conducted of gas diffusion into oil with NMR. And so for that, we take advantage once again with our non-magnetic pressure vessel. But this time, instead of inserting a sample inside the pressure vessel, we will just inject oil and gas inside. And the oil and gas phase will be maintained at the same pressure using these pumps. Why are we maintaining them at the same pressure? Is so that now the mixing between the oil and gas phase will not be driven by a pressure gradient, but it will be driven by a concentration gradient, and so by diffusion. And from there, we can extract the diffusion coefficient of of gas in the oil phase. Actually, we can even get the vaporization coefficient as well. However, to do this kind of measurements, you will need a little more specialized NMR. That will be an NMR that has a gradient coil, because a gradient coil allows you to focus your NMR measurements at different spots along the length of the pressure vessel or along the length of your sample. So we will need an NMR gradient to do a gradient profile measurements. And so when we do that, then now we can track our oil and gas interface, which happens to be over here at 0.75 centimeter over here. And so we can see on top over here, we have a low NMR signal, which represents a low NMR hydrogen index. That will be the gaseous phase. And the high hydrogen index will be the oil phase. The hydrogen index is essentially really just a proxy for a density, right? So it makes sense that the low hydrogen index, which will be low density, will be the gas phase, and the high hydrogen index, which will be the high density, will be the oil phase. Okay, now that we have reviewed this schematic, let's look at some of these actual measurements which we conducted. So these are actual measurements that we did, where we're looking at now methane diffusing into a crude oil as function of time. And so if we look at this, we have the gas phase on top over here, and we have the oil phase below the interface over here. So this red line represents our first measurements in about 0.2 days, so on the first day. And we completed our measurements after 7 days. This will be this dark blue line. And so what we see is that the hydrogen index has reduced quite a bit in the oil phase as a function of time, and that makes sense, right? Because as we are injecting gas, we will expect to see a reduction in the gas, in the oil density as a function of time, because now we are getting more and more gas into the oil phase, and so that's what we do also observe. And so if we look at now, if we zoom in at different spots along the length of our pressure vessel in the oil phase, we can pretty much look at these concentrations as function of time. And that's what we plotted over here. So we can definitely see a reduction of hydrogen index as a function of time, which is what we expected. And using these curves, we can extract our diffusion coefficient. And in this case, we computed our diffusion coefficient to be 7.5 times 10 to the minus 10 meters squared per second. And so we can see that with NMR, we can pretty much do a complete Shale EOR evaluation. And based on this, I think I'll summarize this talk, because I think that's the last application I want to share with you as of today. So to summarize this talk, we have seen that NMR methods can allow you very accurate measurements of both oil and water volume during laboratory EOR processes or experiments, which is something that's almost impossible to do with other methods. And so that shows that NMR is pretty much one of the only ways that you can use to measure accurately really this volume produced during your EOR process. So the key here is that instead of focusing on quantifying what has been produced, we look at really what remain in the sample. So if we do the measurements before and after, then we can get a good idea of what has been produced. That's how we do these kind of measurements. NMR can also be used to evaluate the recovery mechanism, right? Because we've seen that we can change the injection pressure profile, look at the type of NMR recovery that we are getting as function of time, and that can be done in real time, so that we can actually understand our recovery mechanism. And we've seen that in the Shale sample that I have shown you in this example, that it was essentially driven by diffusion. And so that means that we should be really focusing on diffusion-driven flow for our reservoir simulations. That's what we should really be focusing on. And we have seen also that NMR can be used to study gas diffusion into oil, right? That's in the bulk phase. We can also do that kind of measurements, especially if we do have a gradient coil. And if we do have access to the bulk diffusion coefficient, which we can obtain from this last point over here, all then we need is a tortuosity measurement, which can also be done with NMR methods as well to obtain the effective diffusion coefficient. So it seems like with NMR, we can really get a full evaluation of the EOR process, really. And imagine if you are doing these measurements with the real-time one, then in a single measurement, you can do actually a complete evaluation, which will generally take months to achieve, and we have to months to achieve with other methods where you also have to combine different kind of analytical tools. Here, a single tool can allow you to do all these measurements, which also will provide more consistency, because with this kind of measurements, you do also, or this kind of projects, you also do want quite a bit of consistency in your data, right? So if all your measurements have been acquired with the same experimental setup, then at that point you can probably have the best consistency, right? And based on this, I think that's pretty much it for this webinar. I hope that you've learned something out of it, something useful about NMR, and I hope that you do see the value of NMRs once it comes to Shale EOR evaluations. And I hope that he has also given you some ideas on how to proceed about Shale EOR evaluations. I would really like to thank once again SPWLA for allowing me to present this webinar, and also thank the sponsors of this talk, which is Green Imaging Technology. Thank you so much. And these are essentially the main two references that I have used during this talk. One of them is a thesis by Son Deng, and another one is a paper that was presented by one of our students, Byung-Ju Min, I believe that was at an EarthTech conference or so. Okay. Thank you. And I will take on this, I will take any questions if you do have any. Thank you so much.